Okay, so we had stopped last class basically just on this kind of yeah. So remember that what we are trying to do is a very very important kind of a relationship in response systems, in linear response systems, where you try to make a connection between the real part of the response and the imaginary part of the response. So we had a long discourse on what that sort of implies and how you can sort of rationalize that in the context of other things in physics. For example, we saw that amplitude, the real part of the amplitude, and the phase, for example, is an imaginary quantity typically, but it actually tells you what the value of the amplitude will be at a certain point of time. And of course, even before that, we were talking about quantum mechanics x and px, and they are conjugate variables, and px is of course minus I h cross del x, and that's an imaginary part. But okay, these are not directly connected with what we are doing now, in the sense that there does not exist and a very clear relationship with them, as we shall see in this case. So here, remember, what we are looking at is finally the response drawn in material uh, due to light incident on it. And the direct response, of course, is the refractive index, is the generation of refractive index, which comes from a complex dielectric constant. And we know that that is directly, the refractive index, of course, has a real part and an imaginary part. One is the real part relates the propagation of any signal or electromagnetic wave through it, and the imaginary part that is responsible for absorption. So what we said at we it sort of ended the last class saying that why this is useful, of course, in the sense that you can actually experimentally, to an experimentalist, it's very useful. Why? Because if you know the for example, if you want to find out things like how a system would sort of absorb at very very sort of high frequencies or something which are difficult to access experimentally, then it is okay if you can actually measure some, the transmission, for example, at even sort of a different frequency, and you can actually, by this relationship called the Kramer's chronic relationships, you can know how it will absorb without really having to measure it. So that is really something very interesting. It is so if you can measure the dispersion in the transmission, you can actually also get to know the dispersion in the absorption, which is a very important thing, because it's an actual measurement. It is not just a vague mathematical relationship. Okay, so we had started. We were just in the preliminary phases, stages of these Kramer's chronic relationships. And before that, I had said, the one of the starting points is that we know that the group velocity, which is the real velocity of signals for a sort of set of signals, because group velocity is important only when you have a pulse, or when there is a dispersion already in the system, when you have pulses having different velocities sort of grouped together. Otherwise, if it's a single monochromatic wave, then group velocity and phase velocity are the same. So we wrote down Vg as this, and of course, I asked you to derive it, and I'm sure none of you have derived. Uh, am I wrong? Has anybody looked how this actually can be obtained? Anybody
Sir,
there who was, huh?
I thought how it can be done, but I didn't actually write it.
You thought.
I mean, it is straightforward.
Yeah,
Like
it is
from
quite
the
straightforward. It's actually quite straightforward. I'll not deny that. Anyway, but you should see, even always you should finally take pen to paper and just do it, because calculations are damn important if you want to be a scientist at the end. Anyway, so even if you know it's straightforward, I think I would still say that you should once do it, or maybe I should give you an assignment where you need to do it. Anyway, so the thing is, very clearly we saw that around resonance, this guy behaves strangely. We saw that, of course, n behaves like a dispersion, spectrum, in the sense that it goes from n minus 1 goes from positive to negative, and as a result of which dn d omega actually is negative with increasing omega, so that we can see that in that case you can actually have propagation signals, at least Vg, certainly going higher than C, because this guy has to basically get less than 1, which it can. And then of course the issue that obviously comes, so we're actually going to show by in this journey of ours, we're going to show that you in the in time space like light cones, they are not possible. Only time like light cones are there, so nothing can propagate faster than C. No signal can go faster than C. We'll actually show that. But one issue that already is there is the fact that there is actually a pole here. So basically, when this denominator becomes 0, so this thing blows up, Vg, which means that Vg, which is d omega dk, is no longer continuous or differentiable in the entire domain of omega, which means that this definition itself is problematic. Okay. So anyway, what we were sort of thinking where we had stopped last class was that we consider, so we are setting up the problem now. At the moment, we are in the setting up phase where we are going to sort of build our arsenal, and then we are going to proceed in the different calculations. So what we are going to do is we are going to basically write down how a pulse kind of moves from vacuum to another refractive index, which is dispersive. And vacuum, of course, n is 1, and for all frequencies, and then we go to a dispersive system. And what we think of is that you basically think of we have a single wave packet. Remember, what we're going to deal now is always wave packets now, because that is only where you have a multiple omegas present, and they sort of travel from vacuum to some finite absorption, finite refractive index dispersive medium. Finite, of course, this is also finite, but this is something which is different from vacuum, of course. Okay, so let's then proceed. And let me just write down the same thing again. As we said, this is basically properties of signals in dispersive media continued. Okay, so what we are going to say is that you have, say, at some so we consider a wave, we consider a wave packet, just something like ui of xt, and at x equal to 0, of course you have ui 0t, and then we have ui of xt. So x equal to 0, you remember, is the interface. So this is my this is what I had. This is basically x greater than 0, then 0, shucks. There is a forbidden region in this thing. You cannot write x less than 0. This is my x. And I say that this is vacuum, and this is my n of omega. Okay. So essentially, because I have all possible omegas, I have to write this as a superposition, where I will basically write something like this. Okay, and integrating over omega. So we essentially just everything. This is fine, right? So see, we are going to enter some kind of a Fourier domain, that is very clear, and this is the way we set it up. Okay. So now let us play with this a bit, because this k is the thing that is very crucial. K is basically containing the refractive index. We know that, of course, k is something like n omega by c, that we know. and that means I can write, of course, this as sum minus infinity to infinity a of omega sum e I. If I take omega c common, I can write this as basically, if I can just write this as x minus ct, x minus ct, okay, and this is essentially, this is nothing but your d omega, and you know that. So this is something which we'll now use, of course, later on. And in a dispersive medium, we know that this is n of omega. So clearly, what we can write at, so that means if I reverse this now, at x equals 0, we have a of omega. We can write that as, so just the Fourier, as we know, is just given by this ui 0 t e to d I omega t dt, right? This is straightforward. Again, I'm just laying down everything, and then we will write, of course, that in a dispersive medium, basically your k is omega by c n of omega, right? And now here, I'm just going to recollect something that we did before. So do you remember when we had this transmission between some kind of n to n dash? What is the ratio of amplitudes? Transmitted amplitude ratio. Does somebody remember that? When you go from n to n dash, yeah. What? So if I say that this is a dash omega by a omega, what is that given by? So it was like basically the reflection is something like which that's for normal, of course, n1 minus n2 by n1 plus n2. What was the transmission? Hmm? Completely forgotten. Yeah. Was this, does this strike a bell at all? Huh? Hey, again, complete silence. Yes or no? Okay. What?
Yes, sir.
Ah, so for n equals 1, this is essentially 2 by n omega plus 1, n dash omega. We can just write that n dash as n of omega. Okay. So, no, wait, let us just write this properly. N dashed, and for dispersive, basically, I write this as 2 by 1 plus n of omega, which means this u of xt, I basically write as something like minus infinity to infinity. This is that ratio 2 of 1 plus n omega, just the same thing, a of omega e to d I omega by c n omega x minus ct d omega. So this is basically the, the how the pulse kind of works, as this is the expression for the pulse, and very clearly that you can see now that we have to deal with the complex plane now. When we basically look at propagation, etc., of this, we have to sort of worked in the complex plane now. That should be very clear already. Okay, and that is where all the fun basically lies. So this is essentially clear that we need to work in the complex plane now. So this is where I sort of lay down what my signals will be, and now we just proceed to so basically we have to understand this guy. Okay, this is the proper, this is the amplitude. So what does it mean? What properties does it have? Does it have any zero somewhere? That is very crucial. That is extremely crucial. Okay, so let us see what we can do about
Uh,
this.
Sir,
Yeah.
in the above equations, is that A or A dash? Because I think you substituted the A dash in the later step.
Oh shucks.
I just wanted to confirm that.
Yeah, this
Uh,
is basically a dash.
okay.
So what we are seeing here, right? So this is essentially going from your a omega is this place. So this is going from this place to that place. Okay. So when you go from that place to this place, so this is basically this is the guy which is your your new thing, right? Your n omega is for this. So what I'm trying to say is that how it goes from vacuum into this. So the transmission is basically given. So this is the ratio, right? And this a dash omega is essentially a omega into this. So a dash is where we are going now, right? A dash is nothing but a omega into this part. A dash is this one. Yeah. So you can say that is, so n dash is the new thing actually. Okay. So n
Okay.
dash is what I'm writing as n of omega. Is that clear, everybody? N dash is what I'm writing as n omega, and a dash is of course the new thing at the this place. Okay. A omega was what we had initially, right? So initially, so just think of this. What I'm saying is initially it was vacuum, right? So this is not changed. That I'm not writing this as n omega by c when I say this is n is 1. So therefore I could easily write this part. But dispersive media, which is this part, this is this n. Let me write, just clarify this. Yeah, I should write this as n dash. Okay. So then here we have n of omega, which basically means this I have to replace. I cannot write this as k. I have to write this as n omega by c into n omega. And a dash is the new amplitude. Former amplitude was a omega. So basically in the new plane, where it is like x is greater than 0, we are basically having this as 2. I mean, this is the new one, a dash, which is what we have at x greater than 0, which is the dispersive medium. Okay.
So UI is in vacuum and the U that you have
Yeah.
written
Right,
is
right,
in.
right, right,
Okay.
right, right. Exactly. We are starting from there, and this is now at in the dispersive medium. Okay. So let us now proceed with this one. Acha. So what we are saying is that initially, say, what is very important is, so we assume that, so what we are saying is that basically this is your, now if I say that your x is moving like this, so you had something that is coming from here, some pulse like that moving in this direction. And what we are trying to say is that we assume that something like the initially we say that this is 0 for t less than 0. This is very important. Okay. And so typically what is the most expected shape or a profile for a wave packet? What mostly used uh, you know intensity profile or whatever is like a bell shaped thing, na? The most commonly used something that we have is a bell shaped kind of a function, right? So like a Gaussian, because we know that all laser beams are like a Gaussian, and therefore that is a sort of a very general sort of shape, that a profile that we can assume for this wave packet. And we just write that then, that uh, would we consider a sort of bell shaped profile for the wave packet. And so, okay, so essentially what we are looking at here are your properties of A omega. This is very crucial. This is what we are doing here. Okay. So for the wave packet, and that means, so let me just draw what we are trying to do. So basically, I'm saying that suppose your this is something like x. Say this is your u, and I'm just saying that this packet sort of it just sort of starts like that, and at t equal to 0, and then it basically just moves like this. Okay, this sort of translates like that at different times. So this is like t equal to 0, this is t equal to t1, t equal to this is your t equal to t2, this is your t equal to t3. So this is the way it is sort of moving in the evolving in the x-axis. And okay, one thing that, okay, of course we have assumed is that here we are saying that there is nothing. Then before before like t equal, it is starting at t equal to 0. Essentially, starting point is t equal to 0. Okay, t less than 0, it doesn't exist. Okay, so what we should just say is, acha, we want a kind of profile which, as I said, looks like a bell shaped. So can I write something like this? So sort of what I'm writing now. So Gaussian, so this is, acha, by the way, this is very crucial. The best book for this, excellent book for this, is Greiner textbook. I think I forgot to tell you this. So I think it's called EM theory or something. No, Greiner. Vishwajit, what is the
Classical
book?
electrodynamics.
Classical electrodynamics. Yes, Greiner, classical electrodynamics.
Chapter 19.
Chapter 19. Vishwajit is very good at this. Chapter 19, classical electrodynamics. This is a very, very nice book. It's very beautifully written, very nicely. There are some steps which are missing, but that we are sort of going to solve everything. So anyway, so let us. So as you know that what we typically assume for Gaussian is that e to the minus x squared, I think. So what sort of Greiner kind of considers this is something like this. This theta t, we are just going to come what this is. So this theta t is the Heaviside function. Anybody knows what that is? Huh? Heaviside function? Yeah. Blank, complete. Yeah. Haven't you come across this somewhere?
So it's a step function.
Yes. It is basically 0 for t less than 0, and it is 1 for t greater than 1. This is a standard thing. So this is basically, if you look at this is nothing but just the exponential ka, if you just expand this, is what you're going to get. If you plot this, is basically, you just think of it now, 1 plus x squared like that. So this is nothing but this, and the reason we write it like this is basically this is considered as a very small quantity, and this is like the sort of bounding thing. So this just prevents this from diverging out. Let me say that. Just keeps this thing finite. Okay, which is an sort of acceptable thing, I guess. If you plot this, I think you're going to get a some sort of equivalent like this. Uh, if you now see again, remember what we are trying to do is laying down the formalism, laying down the basic approach by which we will proceed proceed with the problem later. But at the moment, as I said, my assumption is that we have these kind of bell-shaped curves which are progressing in time, which were starting from t equal to 0. And I'm saying that it is because it's bell-shaped, it kind of should look like an sort of exponential. It can diverge away, but so that does not diverge, I sort of just put this thing as some kind of bounding thing, and you may plot this, and I think you will get whatever something like this here. So now if I put this guy into what I had for a omega, then what I will clearly have is something like minus infinity to infinity a t to the power m by m factorial e to the minus epsilon t e to the I omega t dt. Remember, this was what we wrote. This is the Fourier transform. So this is where I start out with. Okay. So I'm just laying down, as I said, I'm building, these are the bricks. These are the bricks that I need to finally, make my building. Okay. Acha, so
Sir,
can somebody, bolo.
how did you write that a t power m by m factorial? And is the sum over m? And
Yeah. So basically, you are assuming that this is essentially this is a series over all m's actually, something like this.
so we are
Okay,
just
so
writing
if
a
I,
power series.
yeah. So if you know, but that what I take, Rohan, is that you can basically write, this is, so Gaussian is this one, right? E to the minus x square kind of thing, right? So I am saying that this is how they kind of see, what we need to finally get is a sort of a system, or rather, sort not a system, basically some kind of a. So remember, we are dealing with poles. What we saw in that d omega dk is that it has a pole, right? So and of course it has to be complex and all. So that is completely okay. But what we are trying to build up is a formalism where my amplitude itself will, I mean, you will see that the moment we solve this, we will get some kind of a answer for a omega, where it is like we will have a pole somewhere. But anyway, at the moment, I'm saying that this has to be a bell-shaped curve. Okay,
No,
so
sir,
if
I,
you
I
plot
meant
this guy,
uh,
you will sort of get that.
the bell-shaped curve should be as a function of x, right? But we are seeing at x equal to 0 at some x equal to 0 at all times. But you're saying that the bell-shaped curve is at a particular time, right?
Yeah.
Uh,
Yeah. So basically, we are saying that it has to be some kind of a uh, 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 no. So when you say no, but yeah, okay. So uh, okay. So you're saying that at uh, mm, mm, at a, yeah.
No, the position
Uh,
is x equals to 0, but the time part is the spread of that function.
yeah.
So
So
when
basically,
t
how,
less than 0, that
right?
function is t to the power m, and when t greater than 0, that function is e to the power epsilon. That is spreading.
Yeah. So basically, what we are saying here is how this should get bounded over time. So it is, if you plot this thing, then it will straight come to this kind of a function actually. So how this is bounded over, as you go sort of, as you sort of go down, I mean, as you evolve in different x's, then if you basically plot this, then this will essentially come towards to something like this. So this is how, I mean, yeah, so you can actually say that this is what the time spread is. So it's like the width, which basically will still be bell shaped. Okay, so maybe you can just plot this. If you just plot this, then you will essentially see that this will still be bounded in this form. Okay, so this is something, yeah. So basically, if I uh, eh, so remember, when I say bell shaped, it is essentially how the envelope moves in time. Okay, remember, this is not really it's not the intensity distribution. I am finally plotting, I'm sort of getting the evolution in time itself. So at each time, it is sort of bounded like this. It is going like this.
So I have a question.
Huh?
So if you're interested in this bell-shaped kind of curve, then why aren't we taking that e to the power minus t square kind of the function?
So that is in the sense, if you
No,
directly
that has a thing. Now, if you take t less than 0, then the
then
function will
right
No, you can
exactly.
define
So
you can
basically
define the
exactly.
domain.
So what
So you
Vishwajit
can
is saying,
define the domain to
exactly
be
right.
no.
Now
So you can
see.
change the domain.
Huh?
You can just
Sorry.
restrict the domain.
domain is a that is different thing. But
That
for
is
the
But
sake
so
of
basically,
generality,
Hitesh,
you have
so
to
if
take
you
all. Na?
Actually, your voice is interrupting.
so basically what Vishwajit is saying, if you take this, is somebody saying something? Hello. There is a female voice which is saying anyway. So basically, remember this is, if I take this one, then this is spread for this, right? This is both minus x and plus x. I can't have that, right? So if I do not want to have that, I don't only want this at positive times, right? So this, remember Hitesh, I will only generate this if I go around x equal to 0. Otherwise, I will get just I mean, this is a problem, right? Only for one byte values of x. So this is
You
something
can,
which I basically enforcing only for positive times, and also going to be like bell shaped.
sir,
So
but
you can
here
take
also you are taking this heavy side function
Yeah. So that
because
is
you
the
only
whole
want
thing,
to define for t greater than 0.
right? But then if I plot this chap, you will see that it will always be a bell shaped function.
Yeah, but you can directly take a bell-shaped function. That's what my whole point is. You
No.
can
But
define
then
this heavy side
But
function,
then this
take the
one, if you
quotient.
now see, if you want to take the bell shaped function for this, you can. So basically, the problem will be, unless you sort of shift the origin. This is valid only when you will get a bell shape only when you have both negative and positive x's. No.
Sir, it won't be continuous if we take e to the power x square with a heaviside function. Like we'll
That
get
is
a
correct.
value.
Exactly. Exactly.
Like
That
in
is
this
very
case, t
correct.
to the power m goes to 0
And
at t equal to
yes, the
So this is
function will not be integrable.
that is exactly. This is going to be bounded, and this is basically for ensuring that you will get continuous and differentiable. Because see, remember, when this blows, this is going to restrict it, right? That is why the good part is, right. So
No,
these are
e to the
basically,
power minus t square won't go to 0.
huh?
No, somebody said that e to the power minus t square is not differentiable.
no. E to the power minus x square won't go to 0 in any finite distance.
Why?
Yes,
Like e to the minus x square, so if you put x is equals to infinity, it will go to 0.
Yeah, infinity, right? I said in any finite
infinity,
distance, it cannot go to 0.
At
right?
what distance?
At
At
any finite,
finite distances. At finite distances is never 0.
if you say at t equal to 0, you're going to put a heaviside function, then
Mm-hmm.
there will be a jump discontinuity at that point.
Exactly. Very correct. Very nice.
Okay.
This is very good. Let us just jot this point.
Also, sir, there won't be summation over m.
No, there is no summation.
There is no summation.
Oh,
So
okay.
see, this is
And
what.
when you put this in A, your limit should be from 0 to infinity, right? Because your heaviside function is 0 for less than
Yes.
for
That
less
is
than 0.
So this will go from 0 to infinity. There's no summation. What it is anything actually that way.
So
But it is
the
limited
amplitude,
between that.
it will have the integration limits from 0 to
Yeah,
infinity.
this is what you have, no?
0 to infinity, sir.
No, why
The
should you?
minus infinity to 0
Because you
part
have
will get
heaviside function.
Yeah. No, but this is yeah. So that's correct. Obviously, see, minus infinity to 0 anyway gets 0, na? I mean, obviously, right? This is finally the correct. I mean, because when we wrote the Fourier transform, we had to write this, na? So obviously, when I take minus infinity to 0, that part is taken care of, no? So this is obviously
no,
then
you did not write
anyway.
the heaviside thing. That's why he is saying.
Yeah, I did not write. Oh, yeah. I'm sorry. No, let me just write this.
Sir, one more thing. I think the graph that you're drawn gives a different picture than you're trying to say. If you plot u as y-axis, x as x-axis, and t as z-axis, and plot the bell-shaped curve at x equal to 0 in the yz plane, uh, that bell curve will propagate along x uh, in that way. But obviously, you can't draw that on board. I
Obviously.
just wanted to make a point that
That
this
is
is
not
giving
bad.
a
Yes, you're saying that if you have a z-axis, then in the xz plane, this is how it will go. They're absolutely right. I think that is correct. So let me just write. This is a very good point.
Can you repeat this point?
Yeah. So basically, what Rohan says that the correct representation of this is if you have a z-axis which is t, and then you sort of propagate. I mean, you say that the wave is propagating in the xz plane. Okay. So what I've done is the projection of this on the ux plane, but the correct thing is you have another t-axis. I mean, sorry, z-axis, which is coming out of the paper, and there you sort of you have this, and then that sort of will represent how this curve moves as a function of t, which is I think reasonable as a statement, right? Isn't it? I think what he's saying is correct, because what I've done is just the projections along the ux plane.
And that 2D projection is also possible. That
Yes.
is there in that book. Yeah.
Exactly.
And they've done that.
Achha, let me just complete this thing that we discussed. It's a very nice point. Will cause a step jump at t equal to 0 and make the function discontinuous. Good point. Okay, very nice. Achha, so can we just quickly, so then this basically becomes 0 to infinity 1 by 2 pi. Oh, and take off this constants out. And just take out a by 2 pi m factorial 0 to infinity t to the power m e to the I omega plus I epsilon t dt. So what is the solution? Can you tell me? Solution क्या होगा इसका? Quickly tell me.
Is this the gamma function?
No, sir, that's a problem because
it's not.
Huh? Yes, you just take minus common. Otherwise, the calculation will be difficult. You just take the minus out and write it like this, that epsilon minus I omega. Then it will be that gamma function. Otherwise,
Epsilon minus I omega. Okay, yes. But
if you take only the minus common.
So you're saying that we, but then iska if I just do by parts, you'll get it, no? I think if you just do it by parts, you'll get it, right? I think it will just, I think what you will get here is something like. I think this is what you're going to get. I think this is what you're going to get.
Yeah, this part will directly come if you use that gamma.
Okay. Yeah, so this is essentially nothing but that. Okay, this is basically, but then Bishwajit, this is the same thing, right?
Yes.
Whatever I do, it is the same thing.
But calculation will be easy.
Okay, whatever. Yeah. So what Bishwajit is saying is that you keep this, you make this essentially epsilon minus I omega, then this is directly mappable to the gamma function. I mean, basically make this, yeah. So that anyway, so this is standard formula again. Can you guys, you want to check this out? This is again very standard. This is not a very problematic thing.
Sir, you did this by parts.
I think it will work if I do it, because I think I just check out if you get. See, this is very close to the gamma function, right? The gamma function definition is basically this. This is basically, if I remember, this is the your this generating function of gamma. I think this is generating function of gamma function. Okay, but I don't know. You may check out and just check out if it works in parts. Okay, but I think this is the generating function of gamma function.
No, so because if we'll do by parts, then we'll get a sum over m. Because you differentiate one this t to the power m, and then integrate e to the power it, and you do it till your m becomes 0. So there will be summation if you're doing by integration by parts.
Okay, you're saying that if I do integration by parts, that we have to check them. But I think, see, basically this is nothing but the derivation of the gamma function. Just check this out. Okay, this part.
Sir, if in gamma function you'll have one term is fine when you're like multiplying I with omega and I epsilon. There one thing is e to the power minus epsilon t. That is your gamma function. That is fine. But what about the part e to the power I omega t?
No, so basically you make a substitution, right? I think if you take this whole thing to be something.
But then you won't get minus.
Won't get minus one. See, if I just look at this one here, so you have e to the, see, but this is essentially a e to the I omega t part. That is just like an oscillating function, na? So that if I just,
so we can just complete the square.
You can just, sorry, what?
Complete the square. I mean, make it as a whole square form, and then there will be some other constant part.
Okay. I think this is close to a. Okay, no, whole square part means what? You're saying that you write this as a what?
Whatever is there in the power, if we consider it as a quadratic in root t.
Acha. That way. Okay. Yeah, that may work. Okay. So maybe, yeah, that may be, yeah. So let me see what I had worked out. It was, so basically, if I see, you have, so see this, if you, so gamma function, it is essentially something like x to the power of something. Let me just write. So it is, if I have something like, oh god, this really got crowded. So you can, so gamma function so let me just write down here. So it is basically 0 to infinity, something like what is that?
So e to the power minus t
alpha x, something like that. No, so that is given by
this is gamma of m
by something alpha m plus 1. No, right? This is the gamma function, right? So then this is directly that. No, this is directly that.
Yeah, that will be directly that if you
This is
take that
directly that.
only that minus common.
So gamma function is basically this, no? So then this is directly this.
But sir, what about the part where you have t to the power m I e to the I omega t?
We are taking the alpha to be complex, so the whole
Yeah,
thing,
yeah. So basically, I'm saying
complex
that
thing
this
we are
is
taking.
this. This is this whole thing I'm taking
E to
to
the
be
power
this.
minus alpha x means that alpha we're taking like a complex number.
Correct. Exactly.
Okay.
Exactly. This is what we are assuming. Okay. So basically, what we are saying is alpha is complex. So that whole thing is basically we are saying that omega plus I. This is what we're saying. Okay. So anyway, so then what then you basically get is then of course these two cancel out, and then you get something like a by 2 pi I to the power m plus 1 by omega plus I epsilon m power 1. Right? So what is very interesting, however, see the takeaway from here is that is that the a of omega, this one, it does not have poles in the upper half plane. That is very crucial, extremely crucial. The pole that you have is at omega equal to minus I epsilon, which is lying in the lower complex half plane. That is extremely important, and that is something which we are essentially going to use a lot. Okay, so this is the main takeaway from here. Okay, so again, so yeah, so basically, if you so basically what we're saying is that for u0t equals a t to the power m by m factorial e to d minus epsilon t theta t. Sorry, this is your heavy side. Basically, I'm saying that a is sort of going as 1 to the 1 by this one. Okay, but the crucial part is very important. A of omega does not have poles in the upper half plane of the complex omega plane. This is extremely crucial, right? But it has poles of order m at omega equals minus I epsilon in the epsilon in lower half plane. That is crucial. And this is basically what we are going to use when we are going to show that no signal can propagate at velocities faster than light. This is extremely important when we are going to do that. This whole property that you're going to have. Okay, let me just make this again. This is extremely important. Okay, so basically this part that you have poles only in the lower complex plane is going to be critical when we are going to do the proof that you cannot have signals propagating faster than the speed of light, and no solutions will exist there. So we will just end today's class by quickly looking at the solutions of what we have, properties of your n omega, because remember, finally our target is basically the refractive index. That is what we are really interested about. The physical, the real physical properties which are going to obey this Kramer's tonic are essentially the real and imaginary parts of n. We are going to see that. Anyway, so quickly let us just write down the properties of n omega, and that we are going to take directly as we wrote down before. is n, and we get basically that n squared is 1 plus, these are again standard things which I wrote down before. This is very clear, I guess, right? So now if this is again, we derived it in detail in the when we did the dispersion of in this dielectric system, right? This is the standard formula. I'm not summing over. There was some summing over and all that. So this is just the without that summing over of all electrons. So single electron. Okay. So then this I can just write down as omega square minus omega this thing plus omega p square. I'm trying to see what am I trying to do? I am just trying to see where the poles etc. of a and omega will lie, because the physical thing that we're going to work on is basically n omega, nothing but that. Okay, so this means this, and very clearly this is some kind of polygon of second order, polynomial of second order, both of these, both this one as well as this one are both like polynomials of second order. So I can basically then write, so second order mane how many poles are there? Second order mane poles kya hoga? What? M is 2, right? So poles will be again, poles are what? Order 2 mane poles are
Second order pole, right?
second order, right? So 2 poles, na?
Yes.
Can we write this? Right? Where your omega A and omega omega B are poles of numerator, and omega C and omega D are poles of denominator. These are very standard things. Okay, so can we find out this? So this is what? So basically you are going to say that your nothing, yeah. So kya bolo?
Sir, what do you mean by poles of numerator? There are only two poles, right? Omega C and omega D.
No. So
Yeah,
this is
numerator, those are the roots of the numerator.
Ah,
Poles
yeah. You are actually right. Yeah, these are not poles. Correct. This is not correct. Yes. Correct. They're not poles, of course. So poles basically, obviously will. So yeah. So what will omega A, omega B mane? क्या होगा? Omega A, omega B will be just ये part को 0. Mane basically your omega square plus I omega gamma minus omega 0 square plus omega p square, that is 0. That means this will basically mean your omega A, omega B are minus I gamma by 2 plus minus this thing. This is quadratic, right? Just omega B square minus 4AC. So this will be omega 0 square plus omega p square whole square minus gamma squared by 4. Right? Then omega C, omega D will be just minus I gamma by 2 plus minus omega 0 squared minus gamma squared by 4.
Sir, how did you get gamma square by 4 in the first one?
Hmm,
Oh, हाँ ठीक है, I got it.
ठीक है ना?
हाँ, it's correct. Like B square.
B square. B square minus 4AC. Right? B square minus 4AC, I'm taking 4 common, and this 2 will get cancelled out, right? So for B square minus 4AC, so basically, yeah, I hai, so that is minus, है ना?
Yeah.
Is okay na?
Yes,
So
sir.
this is just gamma minus gamma square plus this one 4. I'm taking 4 common, so then this will be by gamma 4, and this is 2. So there is a 2 below. So ye 2 cancel, and here is gamma by 2. Everybody, is this clear? Clear, straightforward, na? So, acha, see, one thing that, see, basically what Greiner says are all our poles. So, I don't know. So, it's probably not fair to call those two as poles, but, well, what is interesting is he has called all of them as poles. So, anyway, so what is very clearly, okay, so convention, if you write that, then you will, no, but what is interesting is that all these roots, poles, whatever you call them, they are all lying in the lower half plane of the complex omega plane. Right? So this is the interesting part. So basically, and this is very nice, no? So these are almost everything is kind of, conspiring for a certain physical thing to happen. It's quite nice. I mean, obviously, the illustration of this is that the finite velocity of light, which we'll see, but somehow it is almost like, it's all of these are just telling you that nature does something, and we are kind of deciphering what nature is trying to say. I find it quite fascinating, right? So this is very interesting that clearly all roots and poles are along the.
Sir, what if one of the pole was in the upper half of the plane? Where would have been the difficulty?
Yeah, you will see. We will see when. Yeah, it's a very nice question. Yeah,
Yeah,
but I
because
cannot
in when we
preempt
did
it.
complex analysis,
Uh,
where there we saw if there are like finite number of poles are there, then
hmm.
we can easily bypass them and do the
I know,
integration.
I know, I know. No, but Hitesh, let us. We will do the thing tomorrow. Na? We will see that finite velocity of light. We will see that. I mean, this is something which is quite interesting. But
Sir, you are
we will see that. I mean, that you will see that there is that thing is important. That you do not have any poles in the upper part. Okay,
sir,
so.
you are
Uh,
saying that this poles of A omega and N
uh,
omega,
uh,
both being in the lower half of the plane,
uh,
will be useful for proving that the signals are actually traveling with
yes, yes,
less
yes,
than c.
yes, yes,
Oh,
yes, exactly. And that is what I feel is very interesting, because when I first studied this, it is like, I of course do not know it, and then I saw the derivation and all, and then it is strangely connected, right? That you have everything falling into place, and then you see that, okay, so see, and sort of, I don't know whether Einstein sort of knew. Of course, see, this whole, I think, if I remember well, just check this out if I'm wrong, but I think this prove this way of proving that all signals have to travel at velocities less than c. I think it was done by Sommerfeld or someone. I don't. I will probably clarify you tomorrow, but I think it was not done by Einstein himself. But the fact that it is so beautiful, that is something which it later on fits very beautifully. Okay, so when this is almost like it is, well, sort of, it is just, yes, you are tempted to feel that this is kind of an intelligent design or whatever, but I would just say that, this is our way of somehow rationalizing what we observe, and this is so beautifully consistent. Anyway, so I will not preempt too much. We will probably end today's discussion just at this stage, that all the poles are in the lower half plane of the complex omega plane, and we just draw the diagrams. But this is very, very interesting, as we shall discover tomorrow. Okay, so let me just draw the diagram. If I say that this is your imaginary omega, this is your real omega, basically, and this is maybe your minus I omega I gamma by 2, then you basically have something like, yeah, you have maybe 4 planes out there, 4 of these points, so something like this is your omega A, this is your omega C, this is your omega B, like this. This is omega T. And why these are this should be kind of obvious, because your omega C is plus 9 and B is minus 9. Yeah, so basically B and D will be here. And because this is higher, this is lower than this is obviously more on this side. And C and A will be at another side. Because again, this is like, so this is Y and your A is more than C. So this is how they all of them look like. Okay, so is this part, this is very important, by the way, guys. This is something which I don't think you guys have looked at this kind of treatment at all. This math, I don't think this is very complicated math, but the design that we will see, where all this will lead to tomorrow, that is quite fascinating. I hope you guys are not getting, understanding the point of doing this. I think tomorrow when we do the class, we will probably see how these are very nicely all associated. So I will just request you. So when did you do your Cauchy integral theorem and all? Did you do it?
Third year, first sem, mathematical
those
methods of physics.
Those are clear, na? Those are absolutely clear, right?
Yes, sir.
Because those we will need. We will need those. And as I think Hitesh was saying, that thing is basically what we're going to do. That when we just bend over a contour and all that, that is exactly what we're going to do. But so I please have those at the at the tips of your fingers and whatever. Okay. So tomorrow we will just look at this, find what this this interesting whatever. I don't think I shouldn't say coincidence. The way these things pan out, this is how these things pan out, and this theory is what basically leads to a very, very crucial, reality in nature and the way we decide nature using physics. And this really shows that how physics also, as I keep on saying, uses a tool of mathematics to sort of try to explain reality. Yeah, so today we will stop here. Any questions? So these things, again, I would request that you guys maybe have a look at this Greiner, because it's very, very nicely written in that book. So maybe just start reading this, as Vishal said, chapter 19. So just have a look. And remember, I think this is we have really now gone into depths of the course. Before this, whatever we were doing were mostly on the surface. Now this is really to the depths. So yeah, let us try and see, let us have discourses. Let us not just have one-way traffic. I really request you, we are not doing contact. We are not seeing each other's eyes. So please be with me. And it's very strange, as I keep on saying, sitting in a room alone with a computer in front of me and keeping on talking, not seeing anyone. This is not even a Zoom meeting. I feel very odd at times. So please, at least don't be ghostly, some strange psyches kind of wandering in space. Please talk sometime, okay? If you just because so that I don't feel that I don't even know if you guys are not hearing me. That is horrible. Okay. Okay. So let us try to make this interesting. This is not the best way, but whatever. Any questions, Bolo? Nothing. Okay. So then,
Sir,
Bolo.
after a point, maybe after we complete this topic, I mean, I'm personally facing this problem that how are we completing topics? I'm not able to connect the dots. So it would be better if you could summarize or
Mhm.
like,
Right, Rohan, that I try to do all the time. Na?
yes, sir,
So
but
see, remember that. Are you talking about this course or generally all courses?
no, this particular course, like after we
Hmm.
complete a particular
Of
section,
course,
where you can,
exactly, exactly. That is a very good idea. See, that is the whole point that I have that schematic, right, where I keep on showing you how to trap a nanoparticle. So again, remember, maybe we'll start next class with that. But remember, what we are trying to do is finally seeing how light goes into an optical trap. An optical trap is, I mean, this is, of course, there can be hundreds of different examples of using what we are finally using at this moment. But the example that I have given you is I have to take light. I have a laser that is putting out light. It is going through all kinds of mirrors, optics. It is going through beam splitters. It is going through polarizing optics. And I'm setting the polarization of the light. And I am having these dichroic splitters, which basically reflect a certain wavelength, which transmit a certain wavelength, right? And all of that I'm focusing using a very numerical aperture, or a very, very small focal length objective lens into a fluidic medium which has these nanoparticles or microparticles, whatever mesoscopic particles dispersed. I'm trying to catch them using light. So these particles that are maybe of some polymer, maybe of some polymer mane, that is like a dispersive, this dielectric kind of thing, which is transparent. Okay, polystyrene or maybe glass or SiO2, all these kind of things. Okay, either that or maybe even gold. Now that has very different properties. Suppose you have gold that will absorb at certain wavelengths. If it's polystyrene, that will also absorb at different wavelengths. We are trying to unravel that. Of course, at the end, we will join all the dots, and I mean, we will sort of hopefully have reached a situation where we know what is to be done in order to optically confine a a mesoscopic particle. All this is going towards that.
yes, sir,
Okay?
at the end we can just like whatever we
Absolutely.
have
No.
done in that apparatus.
Whenever, guys, I'm very happy you asked this. Whenever you feel confused, just ask me this. I will go through this endlessly. I think it is crucial because most of our courses do not really tell you why you are doing the course. Okay, so I that is why I dug out this example. That is why I'm trying to go through it again. I try to start classes with that. If you want, maybe tomorrow again we will start like this. Okay, and anywhere you feel confused, why you sort of lost the path, lost the track, immediately ask me. But again, I will request you, don't do it in the middle of the class. Either before the class, it's best. Even after the class like this, that's also fine. But please be with me. Okay, otherwise it's going to be just meaningless. Okay, so maybe tomorrow again we will just show that picture that I have, and again have a little discourse. Again, as I
Yes,
said, this is seriously compromising on the content, but I mean how much I can cover and all. But as I think Rohan or somebody, I think somebody said that we
sir,
do have Fridays and all. Ah,
maybe not now. After we complete this disperse like properties of signals in
dispersion. Ah,
dispersion. Uh,
ah, ah.
so after that, I understand what is the experiment is. I
Hmm,
just want to know that whatever we have like discussed or derived,
hmm.
where that is used in the apparatus, not the
Sure,
experiment.
sure. Absolutely, absolutely. That is what. So right, side. Let us finish this, and okay, you're good. But I can also tell you that this part is a bit. This is quite heavy. I mean, this part till now, whatever we have done, this is the heaviest part. Absolutely no doubt about that. Demonstronic is the heaviest part. So if you get again, maybe we need to take at times diversions as well. It is not very simple. And this is something which you guys have never, not even heard of before. I think most of the things that we are doing, at least you have heard of before. This you have not even heard of. Okay. So, but then I will probably even talk about specifically this in tomorrow's class, where exactly you're talking about this. I think it's difficult to write, but since we are recording all these in the video, so maybe that will be useful. So okay, I maybe next class to I will just give you a very small introduction about where exactly this is useful in terms of the apparatus that we are using. Okay, just this part, only this part.
Okay.
Okay, okay then. Okay, chalo, bye for today.
Thank you, sir.